Okay, so continuing on our discussion with recurrence relations, related ideas, the idea of divide and conquer algorithms. And we're going to take a look at some of these. Basically, we can divide the algorithm up into smaller versions of itself and solve those smaller versions and then build it back up to get the final solution. So again, the key idea is to divide the problem into one or more instances of the same problem of smaller size, and then conquer that problem by using the solutions to the smaller problems to build back up to the original problem. And some examples of these types of algorithms are fast integer multiplication, binary search, and algorithms such as merge sort. So suppose that a recursive algorithm divides a problem of size n into a different subproblems, where each subproblem is of size n divided by b. And then suppose that we have some extra operations in order to combine those solutions again in the conquer step. Then f of n is the number of operations required to solve the problem, and f of n is a times f of n divided by b plus g of n. And hopefully that'll be quicker than the naive algorithm. So an example is that you may have seen and probably saw this in CS150 is that of binary search. And binary search is actually really tricky. The first version of this in terms of a program appeared in 1946, which was shortly after the advent of the electronic computer. I'm certain that the algorithm existed before that, but the first coded version appeared in 1946. The first version that was actually free of errors didn't appear until around 1962. So that's 16 years that it took us to code that as a field. And there were some studies done, one in particular, Pattis from the Special Interest Group on Computer Science Education in 1988 showed that about 90% of professional programmers failed to code this routine correctly, even after working on it for a full hour. So it's not an easy algorithm, even though it's fairly easy to describe. It's difficult to code. So you have to make careful choices of variables, preconditions, and invariants to ensure its success. So the main idea with binary search is when you're searching an ordered list, and it is important that they have to be in order, otherwise you get sequential search. You compare the target to the key in the center of the list. If it's smaller, restrict to the first half, otherwise search in the upper half. And keep repeating this. In this way, at each step, we reduce the length of the list to be searched by half. So, again, this is looking for like a page in a book that followed the, a well-ordered sequence of the natural numbers. Again, we keep two indices, the top and bottom, that will bracket the part of the list that's still to be searched. So, we might start out between 0 and 1,000. We're looking for page 375. So we would restrict our search to the first half of the book between 0 and 500. Then we would look at page 250. That's too small, so look between 250 and 500. The next one would be the midpoint there, which would be 375 when we found it. So in order to think about this, we need to think about an invariant, and that's the statement that's going to be true before every iteration of the process. And they're an important part of proving properties about algorithms, mainly correctness. Dijkstra and Grice wrote a book called The Science of Programming that was written in 1981 that covers invariance in quite a bit of detail, as well as proving program correctness. We also covered a little bit of this in section 4.5 of the text in CS141. So for binary search, the invariant is the target key provided provided it's present, will be found between the indices bottom and top inclusive. So for our initialization, we set bottom to 0 and top is equal to list size -1. Compare the target with the record at the midpoint, and then change the appropriate index top or bottom to restrict the search to the appropriate half of the list. And the loop will terminate when top is less than or equal to bottom if it hasn't been terminated earlier by finding the target. And we make progress towards the termination by ensuring that the number of items remaining to be searched strictly decreases at each iteration of the process. Now, there are two versions of binary search, oddly enough. The first version is the forgetful version. And this one says, hey, forget the possibility that I locate the you know, target right away or the key and continue to subdivide the list until what remains has length one. At that point, I will have found it or report back that it's not there. And so basically, when the middle part of the list is reduced to size one, it'll be guaranteed to be the first occurrence of the target if it appears more than once in the list. So this is the forgetful version. And when the middle part of the list is reduced to size one and hits the target, this will be the first occurrence of the target. The recurrence here is not symmetrical since the condition tested puts mid into the lower of the two intervals, and integer division is going to truncate downward. So this guarantees that the recursion will terminate. We also see the size of the interval steadily decreases, and we check to see whether or not we found it at the end. We can also make this into an iterative version, and that's found on page 283 of the text. Mr. Smiley doesn't forget, but this version certainly does. The one that you're probably more familiar with is the one that's recognizing equality. And so if we manage to locate it, then we return that location and terminate the algorithm. So this one checks at each stage to see if the target has been found. And this one requires two comparisons of key, whereas the forgetful one only requires one comparison. So it's actually slightly more efficient to forget, which is kind of unusual, but if you think about it, you're not making as many comparisons. So binary search reduces the problem size n to size n divided by 2 using those two comparisons. Divides the half of the list to look in and determines if anything is less. And so we have this recurrence relation, f of n is equal to f of n divided by 2 plus the two comparisons. And we assume n is even. Another example is merge sort. And you've seen sorting in 150 and 151. And sorting, things like selection sort, bubble sort, those can be kind of fun, but they're not the most efficient sorting algorithms. And merge sort basically says, hey, I know how to, I'm not the smartest individual on the planet, but I can sort one item. And that's the idea behind merge sort, is we basically divide the lists that we want to sort into two lists at each stage of the process, and then we continue to do this until we get a list of size 1. And then that list is automatically sorted, and then we build it back up. So the other divide and conquer sorting algorithm is that of quicksort. And quicksort is slightly different. We choose some key from the list. You usually try to pick a midpoint as the key. And we call that key the pivot. And then we move everything that's less than that into the first list and everything more than that into the second list. And then we continue to do that until we break it down into lists of size 1. Quicksort can run into some problems, particularly if you choose the worst possible choice at each stage. So, if I choose largest item, then everything goes in the smaller list. If I, again, take that smaller list and choose the largest item, everything again goes into the smaller list, and I end up with a selection sort. But in general, quicksort is going to work much faster than selection sort. There are just bad cases where it could end up not being the most efficient algorithm. So for merge sort, consider this list: 26, 33, 35, 29, 19, 12, and 22. Chop it into two lists at the midpoint, and we're going to make the left ones slightly larger. So we get 26, 33, 35, 29, and on the second list, 19, 12, 22. We again apply that recursively and chop that first list into 26, 33, and then 35 and 29. Take the 26 and 33, chop it up, 26 and 33, 35 and 29. And then we merge the list back at each level. So, there I would take 26 followed by 33, 29 followed by 35. Then I would merge the two lists, 26 is the smallest, so put 26 in there. Now it's 33 or 29, 29, 33 or 35, 33, and then 35 goes in. And now attack the right-hand side in a similar manner. And so here's the recursion tree for merge sort. The originals are in black, and the sorting step goes back up the tree, and those are depicted in red. So this algorithm splits a list of n items into two lists of n divided by 2 until we get that list of size 1. And then we successively merge the pairs of lists. Successive merges are done until the entire list is put into increasing order. And assume that each step divides the list by m divided by 2 and uses less than n comparisons to merge the list. Then we have the recurrence relation. The m of n is equal to 2 times m of n divided by 2 plus n. Another place where we use divide and conquer algorithms is fast integer multiplication, and this will work for binary numbers. And basically what this one is, we're splitting the n-bit binary integers into smaller blocks and then doing some more additions rather than the multiplications. So each of the two n-bit integers gets split into two blocks with n bits, and then we do 3 multiplications of these n-bit integers versus the 2n, along with some shifts and some additions. And you've seen this perhaps in 266. In this case, the following recurrence relation defines the number of bit operations necessary. It's 3 times f of n divided by 2 plus c of n, which is the additions, subtractions, and shifts, which is a constant. Another example that you'll encounter of the divide and conquer algorithm is fast matrix multiplication. And if you've done some of the matrix multiplication in section 3.8, hopefully at this point, then you'll know as those matrices get bigger, it takes a lot more work to do them. And in fact, it's O of n cubed. So, if I assign you multiplying 2 by 2, not so bad. 5 by 5, that's going to take a lot more work. So we would have n cubed multiplication, n squared times n minus 1 additions. So that's a lot of work. Strauss in 1969 figured out how to reduce the problem to multiplying 2 n divided by 2 matrices and then doing 15 additional additions. And if you've done some work in numerical analysis, multiplications and divisions are long operations, at least in terms of the computer. And so that the additions are faster than the multiplication. And again, that's something we see in 266. So the recurrence relation here is 7 f of n divided by 2 plus 15 n squared divided by 4. And the algorithm for this one isn't given in the book, but there's a link section to the example. So there's some online material, and I'm certain that you could find it at a good reference site. If you wanted to see how Strawson actually coded this up. So is there a pattern here? Well, obviously, if I'm putting a slide up there asking if there's a pattern, there's going to be a pattern. And in fact, these recurrence relations are the form a times f of n divided by b plus g of n, just like we talked about in the intro slide. And it's possible to derive estimates of the size of the functions or the growth of the functions based on these recurrence relations, and we get a theorem to do it. And so here is theorem 1. Let f be an increasing function that satisfies the recurrence relation. F of n is equal to a times f of n divided by b plus c. When n is divisible by b, a is greater than 1, and b is an integer greater than 1, and c is a positive real, then f of n will fall into O of n to the log b of a, or O of log n when a is equal to 1. And when n is equal to b raised to k, where k is a positive integer, f of n is given by this form c1n to log base b of a plus c2, and we have the formula for c1 and c2. So as an example, let f of n be 5 times f of n divided by 2 plus 3, and f of 1 is equal to 7. Find f of 2 raised to k, where k is a positive integer, and then estimate f of n if f is an increasing function. And again, we use theorem 1. Here a is 5, b is 2, and c is 3. If n is equal to 2 to the k, then f of n is equal to a to the k, f of 1 plus c divided by a minus 1 plus minus c divided by a minus 1. And basically here we get f of n is 5 to the k, 31 divided by 4 minus 3/4. And if f of n is increasing, then it's O of log base 2 of 5 by theorem 1. And that's slightly larger than O of n squared, but not too much. And hopefully that's better than O of n cubed or O of 2 to the n, that we might get with the naive version of the function. For binary search, we can use that theorem 1. And again, this is nice because a is equal to 1. And so f of n is O of log n, which, corresponds to our natural understanding of binary search. This leads us to what's known as the master theorem. And boy, I would love to cite master of puppets here, but probably don't want to do that because I would get a cease and desist letter from Metallica's lawyers, and I'd rather get just a nice letter from Metallica themselves, which I doubt that I'll get. So let f be an increasing function that satisfies the recurrence relation. F of n is equal to a times f of n divided by b plus c times n raised to the d, where n is equal to b raised to the k, and k is a positive integer. A is greater than or equal to 1, and b is an integer greater than 1. C and D can be real numbers with C positive and D non-negative, so D could actually be 0. And in the case where A is less than B raised to the D, we have the order of magnitude being O of n raised to the D. If A is equal to B to the D, then we have n raised to the D log n. And if A is greater than B to the D, it's O of n log base B of A. So for merge sort, A is 2, B is 2, C is 1, and D is 1. And in this case, we get merge sort as O of n log n, which again kind of corresponds to our understanding of how that works, because you have n leaves in the tree, and the tree is of height log n. So it's nice that this, works out in the way that we expect it to. For the multiplying two n-bit integers using the fast multiplication, we actually get O of n log 3, which, is not quite n squared, but it's better than the n squared that we had originally. So this is a faster version of it. And then last but not least, the number of multiplications and additions required to multiply two n by n matrices using the matrix multiplication that Strawson came up with the additional additions and the n divided by 2 matrices. A is 7, B is 2, C is 15 over 4, and D is 2. So it's O of n log base 2 of 7, which is less than O of n cubed. And so that's actually more efficient than our original. So it works out very well for us. Again, thanks so much for watching.